Hello and welcome again. Today we focus on structure 1.3 for IB Chemistry HL and SL first exams in 2025. And of course, I want to take this opportunity to give a shout out to all of my former students out there at the Canadian International School in Bangalore. You guys are in IB2, year 12, and you will be sitting for the exam in May. Of course, I miss all of you, wishing all of you well, and please do look out for my tips that will be coming your way sometime very soon. Some tips for the May 2025 exam. That, of course, is a very important exam. It's the very first time that this new chemistry guide will be examined. But now let's take a look at electron configurations. And of course, we are supposed to be studying about emission spectra produced by atoms emitting photons when electrons in excited states return to lower levels. So we must do this against a background of understanding about the electromagnetic spectrum, its layout, what do all the colors mean, all the sections, and the wavelengths and the frequency. And then we'll go on to distinguish between what we are very familiar with, which is the continuous spectrum, and we're going to compare that to a line spectrum. Specifically, just one line spectrum. We don't need to look at the line spectrum of multiple elements, just the line spectrum of hydrogen. And very significantly, the line spectrum of hydrogen provides evidence for the existence of electrons in discrete energy levels. It provides evidence for the Bohr model of the atom, which places electrons in discrete energy levels, the first level, the second, the third, the fourth level, and so on. Bohr model of the atom suggests that electrons exist in distinct energy levels or shells. And the emission spectrum of hydrogen supports this idea. So let's take a look now at how it supports this idea. Here we can see this red plus sign in the middle representing the nucleus. And then we have all of these energy levels. And one of the things that students would normally ask, how come we have all these energy levels? Doesn't hydrogen just have one electron and it's in the first shell? Why do we have all of these shells? And I want to emphasize that these are not shells in the sense of the Bohr model of the atom. But the Bohr model of the atom does say that electrons can exist in discrete energy levels. And here this model is going to provide empirical data to show that, because we can take hydrogen gas and we can put it into a tube and run an electric current through it. And when we do that, we observe four distinct lines, as you can see here in this insert. Now, these four lines, how do they get produced? We want to get a better understanding of that, and of course related to our understanding of the electromagnetic spectrum. The electromagnetic spectrum shows various wavelengths and frequencies of electromagnetic radiation. And in the middle part of that spectrum, you have the visible spectrum, which goes from violet all the way to red, or as we say, VIBGYOR, or if you want to go from red to violet, we say Roy G. Viv. But going in the VIBGYOR direction, we see that violet has the shortest wavelength and the highest frequency. There is an inverse relationship between frequency and wavelength, and when you multiply frequency by wavelength, you get 3.0 by 10 to the power of 8 meters per second, the speed of electromagnetic radiation, or what we might call the speed of light. Any type of radiation, not just the visible radiation, not just what we call light, but UV radiation, which would be on this left side here, gamma rays and X-rays, all the way down here with the really short wavelength and really high frequencies. And then over on this side with microwaves and radio waves, really long wave radiation that have very small frequencies. They both would come up to the same answer for the speed of electromagnetic radiation, or the speed of light. But we are focused on the 4 lines in the visible spectrum of hydrogen, the line emission spectrum of hydrogen. Hydrogen gas put into a chamber, high electric current run through it, the light that's emitted is analyzed, and we see that there are 4 distinct lines actually produced. With the naked eye, it looks like this purplish color. But when we split that up with a diffraction grating and we look at it, we will see 4 distinct lines. And these 4 lines are produced because electrons get promoted when electrical energy is given to the system to higher levels. And here we see an electron transitioning from level 6 to level 2. You can count here and see 1, 2, 3, 4, 5, 6. And when this happens, it corresponds to a packet of energy or a photon that is just about 410 nanometers in wavelength. And you can get the corresponding frequency, multiply the frequency by the wavelength, and of course you'll get the speed of light. But this wavelength is in the violet part of the spectrum, very much on the border between ultraviolet and visible. What about if the electron transitions from n equals 5? Notice this arrow slips across to something more in the blue area of the spectrum. And I know this looks violet, but it actually should look blue. And then what about if the transition is from N4 to N2? Then you'd get a line in the green part of the spectrum. And here again, the color doesn't quite match, but it should be in the green part of the spectrum, 486.1. And finally, N3 to N2 would give you a line in the red part of the spectrum. Again, you have 4 lines that make up the line emission spectrum of atomic hydrogen. A violet line, a blue line, a green line, and here we have the red line. All of these lines in the visible part of the spectrum result from transitions from n equals 6, n equals 5, n equals 4, n equals 3 to the level n equals 2. That brings about lines in the visible part of the spectrum. This is also known as the Balmer series. Now, what if transitions went to n equals 1 from higher levels? And here you can see a transition from N3 to N1, and immediately you see this wave pattern here looking very much different, really compressed, with the wavelengths being very, very small. So you get high frequency and short wavelength when you have transitions to n equals 1. And what about if you have transitions from higher levels to the level N3? This results, as you can see here, in big wavelengths and low frequencies. These lines typically would end up in the infrared part of the spectrum, and they would lead to a series known as the Paschen series. And for the lines that go to N1, that gives the Lyman series. These names are not required, and what IB chemistry students need to focus on particularly is the line spectrum of hydrogen, the visible components of it, and to know that for the 4 visible lines, all transitions end up at the level n equals 2. If transitions end up at the level n equals 1, we get lines outside of the visible spectrum, in the ultraviolet part. And if transitions go to n equals 3, we get emissions in the infrared part of the spectrum, bearing in mind that all of these emissions are electromagnetic radiation. And for each type of radiation, if you multiply its frequency by its wavelength, you will get one answer consistently, which is the speed of light, the speed of electromagnetic radiation, 3.0 by 10 to the power of 8 meters per second. But one of the things shown in that model that could be a little misleading is the size of the energy gap between N1, N2, N3, N4. And this diagram here is much better at showing you all of these lines and the colors that I mentioned. But what we notice is that as you go from N1 all the way to N6 and N7, the gap between one energy level and the next becomes much smaller. And if we keep measuring transitions from higher levels successively after n equals 7, the lines are going to become so close together that we reach the limit of convergence, or we call that n equals infinity. And that's a very, very important point to note as we look at how this evidence could be used to determine ionization energy, or the energy needed for an electron to escape its atom and to form a positively charged ion. But that would be the subject of another lesson.